Hello everybody. Today we'll talk about how hard it is to attack Safari in 2022. My name is Quentin Meffre. I do vulnerability research and exploitation at Synactive. And if you doesn't know Synactive, it is an offensive security company. Today we are more than 100 ninjas and we are hiring. Today, building a full chain targeted the iPhone using the browsers as an entry point required at least 2 stages. The first is used to build a code execution primitive in the web content process, and then attackers must find a way to escalate privileges to access sensitive data. This talk is about the first stage, getting code execution in web content. Compromising Safari involves different steps. Oftentimes, attackers start with 2 different primitives, ADDOF and fakeobj. Both primitives are used to leak the address of an arbitrary JavaScript object and build a fake object in memory. And then attacker will use this primitive to get arbitrary read-write. And then attackers will have to bypass many mitigation like PAC and APRR. And at the end, attacker reaches arbitrary code execution. In this talk, we will see that Apple harden each of the steps. The first mitigation added by Apple in Safari has been shipped in 2016, while the last one has been introduced this year, so in 2022. And Apple added a sum of 7 different mitigation in Safari. So the first mitigation was separated WX heap, and this mitigation has been designed to stop attackers from overwriting the JIT page. Now the JIT page is mapped twice. One page has protection read and execute, while the other one has protection read and write. And at the runtime, a function is cheated using the JIT engine, and this function is write on memory pages that has only execute protection, and the address of the JIT page that is writable is inlined into this function. And this function is used so to write data into the JIT page. And because it is in a memory page with X-only protection, attackers cannot usually leak the address of the JIT page with read-write protection. But without control flow integrity, this mitigation was easy to bypass. An attacker just has to build a call primitive using ROP or ROP or job chain, call the JIT write separate heaps function, and then attacker will write arbitrary code into the JIT page. Then Apple quickly replaced this mitigation with a hardware mitigation named APRR. Now the protection of the JIT page are switches using system registers. So even if the JIT page has protection, read, write, and execute, if the value in the system registers, in the APRR system registers, is not the one used to say that the JIT page is writable, if an attacker tries to write into the JIT page, the processor will raise an exception. And another method to bypass APRR was to jump in the middle of the function that set the system register. But now this method doesn't work anymore because the system register's value come from read-only pages that is shared with the kernel. So an attacker cannot write into these pages. And after setting the system register, the value of the system registers and the one stored into the read-only pages are compared, and if they are different, the process crash. But like the previous mitigation, if without control flow integrity, this mitigation can be bypassed by calling the function that write data into the JIT page, and attacker will write arbitrary code into the JIT page. And then Apple starts to kill arbitrary read-write methods. The first mitigation that killing method was the gigacage. Before the gigacage, attackers often used the type array, which are JavaScript objects used to read and write arbitrary bytes into a data buffer. But now, and so if attackers can corrupt the data buffer of a type array, then attackers could usually read and write to arbitrary memory. But now, with the gigacage, type array are allocated in a 32 gig zone, and this zone is followed by another 32 gig zone allocated with a part_unknown protection. And of course, the typed array doesn't store the address of the data buffer. Now it is an offset to the cage, and all this protection kills the method of using the typed array to build arbitrary read-write. But this mitigation is pretty old now, and some other method has been found since this mitigation. One known method is to use the other object than the typed array to build arbitrary read-write. One interesting note is that today, on the latest iOS version, the gigacage is not enabled anymore, but we will see later in this presentation that another mitigation is used to stop this method. Then Apple introduces structure ID randomization to stop attackers from building fake JavaScript object. To understand this mitigation, it is important to know how JavaScript object works. Each JS object inherits from the JS cell object, and the 4 lower bytes are the structure ID of the object. This structure ID is just an index used to get another structure named the structure of a JavaScript object. And of course, if an object has an invalid structure ID, then the process will crash. Before the structure ID randomization, this structure ID was an index incremental, and it was easy for an attacker to build a fake object with a valid structure ID. But now Apple introduces 4 random bits in the structure ID, and this signature is checked many times. For example, when the JavaScript engine gets a property of an object, or when the garbage collector scan JavaScript object, then the structure ID is often used. But sometimes the structure ID is not used, and this behavior leads to some structure ID randomization bypass. Today, structure ID randomization has been removed, and the structure ID is just the low 32 bits of the structure pointer. Then Apple introduces an hardware mitigation named pointer authentication code. This mitigation has been introduced by the ARM standard version 8.3-A, and this mitigation prevents an attacker from corrupting sensitive pointers. Now signature is added to some pointers, and if an attacker tries to corrupt a signed pointer without signing it correctly, correctly, then the process will often crash. Some new ARM instructions are now used in Safari. For example, we will have the pack instruction used to add a signature to a pointer, the auth instruction used to check and remove the signature from a pointer, xpack are used to remove the signature from a pointer, ret_a are used to return to a signed address, and BRA and BLRA are used to branch to signed pointers. Pack can be used to sign two kinds of pointers, the data and the instruction pointers. And for each kind of pointers, two keys can be used, the A and the B key. And oftentimes, context is also used to avoid pointer substitution. But also, sometimes null context can be used. We will see later why it is important. The signature is stored in the top bits of a pointer, and the signature length will depend on the key and pointer kind. So for example, data pointers has a signature of 16 bits, while instruction pointers has a signature of 24 bits. Some example of pointers signed in Safari. From the instruction pointer side, we have each vtable function pointer that are signed with the pack_ia instruction, each return value stored on the stack, and each JIT code pointers are signed with the pack_ib instruction. And from the data pointers side, we have every vtable pointer signed with the pack_da instruction. We also have some sensitive data pointers that are signed with the pack_db instruction. For example, the data buffer of a typed array is now signed using pack. This is why attackers still can't use a typed array to build arbitrary read-write. And also, JIT instructions are signed with the pack_db instruction. Today, almost every instruction pointers are signed with pack, and many sensitive data pointers are also signed. But since pack have been introduced, some public pack bypass have been disclosed, but each of these pack bypass have been fixed by Apple by improving both the hardware and the software. One of the first pack bypass disclosed was a design issue in the implementation of pack. If a pointer authentication failed, then before the signature was removed and one of the top bits was flipped. But this operation didn't raise any processor exception. And after this pointer authentication failed, if the pointer was signed again, then the processor will process the correct signature to the pointer with just one bit flipped. Then an attacker just has to flip this bit to sign arbitrary pointers. But now, since A14 processor, Apple implemented enhanced pack, and now signing an invalid pointer will totally discard the signature, so attackers cannot leak anymore the signature. But one bypass was still possible. Attackers could still brute force the signature of pointers, but again, Apple killed this method. Now the compiler option -fptr-off -off is used, and with this option, check is added after every auth instruction. And if the signature given to an auth instruction is invalid, then the process crash. And since A15 processor, Apple totally killed this kind of bypass, because now if an out instruction fails, then the processor raises an exception. Initially, many pointers were signed with a null context, and potential bypass would be to change pointers signed with a null context, like we could do in a job chain, to build powerful primitives. This kind of bypass has never been seen publicly, but since iOS 15, this kind of attack has almost been killed, because now very few pointers are still signed with a null context. Many more pack bypass have been published, but Apple fixes all of them, and today there is no public way to bypass pack. Before 2022, pack was not used to sign many sensitive data pointers, and one known method to build arbitrary read-write was to use some DOM objects that are wrapped into JavaScript objects, because if attackers can fake this kind of JavaScript object, then it can control the wrapper pointers to the DOM object and potentially build arbitrary read-write. One interesting object was the DOMRect, because it has 4 double, and it also has methods to read and write these doubles. So if an attacker can fake this kind of object, it can read and write arbitrary doubles to memory. This method was used by a public exploit of 2021. But since iOS 15.4, this method and many more have been killed, because today many wrapper pointers are signed, and of course most of the signed objects were objects that allow to manipulate floats and double, and these fixes killed many arbitrary read-write methods. Then Apple introduces the JIT code signature. Before this mitigation, when the JIT engine compile some codes in another thread, it always store temporary generated instruction in a temporary buffer, and at the end of the compilation, the JIT engine write the contents of this temporary buffer to the JIT page. So before JIT code signature, a way to bypass pack was to raise the JIT thread to put arbitrary code into the temporary buffer, and then attacker will write arbitrary code to the JIT page. But the JIT code signature killed this method. This mitigation is a software mitigation based on pack, and now each instruction stored in the temporary buffer are signed with the previous generated signature and the packdb instruction. And of course, each generated signature are checked just before writing into the JIT page, and if one signature is invalid, then the process just crash. But one issue still remained in the JIT code signature. Before 2022, the hash used to sign the next instruction was not signed and was not protected. And corrupting this hash may lead to some issue. But since 2022, now this hash is signed with a unique identifier named the pin. Of course, each JIT compilation uses a different pin, and each pin information are stored in the JIT page, so an attacker cannot corrupt the pin information. Like Luca Todesco said this morning, in 2022, Apple introduces the JIT cage, or also it is named the JIT box. In Safari it is named the JIT cage, but in the kernel it is named the JIT box. And this mitigation stops attacker from calling arbitrary function from the JIT page. Now the JIT page is mapped with a new flag. We doesn't have the name of the flag. I will name it map_JIT cage. And if you look at references about this flag in the XNU open source project, you will not find any reference. But if you look in the kernel cache, you will find how this flag is implemented in the mmap syscall, and you will quickly find a short function that set two new system registers. The value used by these system registers are the size and the address of the JIT page, and maybe some flags. And the kernel cache doesn't have any other information about the JIT cage. So the most interesting part of the JIT cage is implemented in the processor. Now the rules change in when an attacker executes code in the JIT cage, because some instruction cannot be used in the JIT cage. Like for example, an attacker cannot execute an unsigned rate instruction or an unsigned branch instruction. Also, attackers cannot use the syscall instruction or setting or reading system registers. And if an attacker tries to execute this instruction into the cage, the processor will raise an exec bad instruction exception. Also in the cage, the pack instruction keys are different, and an attacker cannot usually sign the instruction pointers into the cage, because when executing pack IA or pack IB, then the processor will just not add the signature to the resulting pointers. Pack IB can be used to sign pointers that points into the JIT cage, and signing data pointers seems not affected by the JIT cage. One last interesting question is that when the JIT engine generates code, the code often calls some function outside of the JIT cage. So how does the JIT engine can call this function? Now a new system register is used, and when the JavaScript engine is initialized, a special value is set in these system registers, and it allows to change the instruction A key of the current process with the instruction A key of the JIT cage. And of course, after doing this operation, the JavaScript engine will sign every function used into the JIT cage. And after the instruction A key is reinitialized with the one of the current process. Now, with this instruction, an attacker cannot usually call function outside of the cage, even if it has arbitrary code execution. Today, building compromising Safari involves finding a vulnerability, a new method to build an arbitrary read-write primitive, and some bypass for pack APRR and the JIT cage. Maybe today one solution for attackers could be to implement the next stage using JavaScript only, because it doesn't need to bypass APRR and JIT cage. In short, in 2022, attackers got yet another mitigation in Safari, and yet other exploitation methods had been killed. In my opinion, attacker can expect the same things for the next years. And I will conclude this talk by saying that maybe it's time for attackers to find another entry point than the browser, or maybe not, because the JavaScript engine is still a very powerful engine to face all this mitigation. Feel free to ask questions at the social event if you have any, and thanks for listening to my talk.